Okay, I've got a problem up here on the board that I want to solve two different ways. We're going to find the displacement of an object over the time interval from 0 to 2. Okay, and here I've given you the position function. The position function is just 60t. Let's suppose t is in hours and p of t is in miles. Okay, and I want to find the displacement using the position. But then I also said, hey, if I take the derivative of position, I know that's going to give me velocity, and the derivative of 60t would just be 60, okay? And I can use the velocity function to also find the displacement. So when we've talked about position and displacement, we've had more than one way of calculating things. Now remember, displacement, by definition, is just the change in position. So this would be my position at my ending time minus my position at my starting time. So at time 2, my position is 120, minus at time 0, my position is 0. Notice I've drawn the graph as if it's defined just from t equals 0 onward. Okay. All right, so that would be 120, and of course that would be miles, because position was measured in miles. Okay. Now, if I wanted to find that using velocity instead, I know that I can find that by integrating. Okay. Because if I integrate velocity, I'm going to get displacement. Now, in this particular case, my velocity happens to be positive, so it coincides with my speed. That's going to mean that my displacement and the distance are actually the same. But as a general rule, if I integrate velocity, I will get displacement. So I can say the integral from 0 to 2 of the velocity function would correspond to just this area, which would be 2 hours times 60 miles per hour. So that's a symbolic area that we have, and that would be 120 miles. So I get exactly the same thing. But notice that what that means is that this integral is exactly the same as this subtraction problem. That's nice. Because in general, I mean, this integral was pretty easy because we were able to do it by just finding the area of a rectangle. But in general, when I want to integrate, I'm chopping, I'm creating a Riemann sum, I'm taking the limit of that Riemann sum. That's a long process. Subtraction, not so bad. So let's explore this just a little bit. What we just saw was that the integral from 0 to 2 of the velocity was the same as the change in the position, because those are both displacement. Notice that velocity is just the derivative of position. That's going to make position an antiderivative of the velocity function. So, let's see. Let's suppose I wanted to integrate from 0 to 2 t squared dt. Well, if I were to think of that as a velocity function, so that it would be the derivative of some position function, then I would know that this integral was representing displacement. But I know that I can express displacement as just the change in position. So if I could figure out what this was the derivative of, if I could find an antiderivative, I should just be able to evaluate that at 2 and at 0 and subtract. Well, let's see. I think an antiderivative of t squared would be t cubed over 3. Now, I don't know for sure. I'm just saying, suppose that's a velocity. I wasn't told that this actually was. If I was told that that was actually the velocity of some particle, I'd have to be given an initial condition in order to find the exact position function. But I can say, if I had a particle that had a position function of t cubed over 3, the derivative of that would be t squared, so that would be the velocity function. So I can say this is just going to be t cubed over 3. Now here's a little bit of new notation, evaluated between 2 and 0. So we've sometimes had an evaluation bar before, but we've usually just been putting a number down here, and that just meant evaluate this function here. When you have two numbers, that means evaluated at 2, evaluated at this number, oops, over 3, minus what you get when you evaluate here. So evaluate at both places, but then subtract the results. So this would be 8/3 minus 0, which is 8/3, and that is the correct answer. That's really cool. That's a very, very nifty shortcut. In fact, it's so nifty that it has a name, and that name is the fundamental theorem of calculus, part 2. Now again, the numbering of the two parts varies. Some textbooks will say this is part 1, and the part that we've already covered is part 2. Our textbook calls this part 2, and the other part is part 1. It says this: if f of x is continuous on the interval from a to b, then the definite integral from a to b of f of x dx is just capital F of x, to be defined in a moment as an antiderivative of little f, evaluated from b to a. Again, that just means f of b minus f of a, where big F of x is an antiderivative of little f of x. Okay. And the reason our textbook makes this part 2 is because part 1 tells us that such a function exists. Remember when we talked about part 1 of the fundamental theorem of calculus, we said part of the significance of this is that even if you have this really wonky function, an antiderivative exists because you could create this area function that would be an antiderivative of any given height function if that height function is continuous. Okay, so that's kind of cool. Now that's the fundamental theorem. The book also restates this as the integral from a to b of big F prime of x dx, because that's what little f would be. If big F is an antiderivative, little f is just the derivative of big F, and this is just f of x evaluated between b and a, which is f of b minus f of a. Okay. Phrased this way, the book calls this the net change theorem. It's the same theorem, it's just a difference in notation, but they're basically saying, hey look, if you integrate a rate of change, you will get an amount of change. We saw that first of all with velocity. If you integrate the rate of change in position, you will get the amount of change in position, otherwise known as displacement. Okay. So that gives us a really nice way of evaluating some definite integrals. We're no longer going to have to chop things up into little pieces and approximate the area of each piece and create our Riemann sums and take our limits, as long as we can find antiderivatives. And back in section 4.9, when we were using this integral sign and calling this an indefinite integral, and then we switched to this definite integral, it seemed like they were two totally different things, because the indefinite integral of f of x dx is a family of functions. It's the general antiderivative of f of x. The definite integral from a to b of f of x dx is signed area. Seemed like they had nothing to do with each other. But now we can see, if this represents a rate of change, that signed area is going to represent an amount of change. And we can find the amount of change by simply subtracting an ending value minus a starting value. But what function do we do? One of these functions. We use one of the functions from this family of antiderivatives. All right, so let's take a look. Let's do the integral from 0 to pi of sine x dx. Now this is one that we couldn't do before, because that's one bump in the sine graph. So we were able to see that if we kept going to 2 pi, we'd get the same amount of negative area and they'd cancel out, but we couldn't do this one before. So what I need is an antiderivative. So back in 4.9, we started to learn antiderivatives. So let's see, I'm thinking, does cosine work? Well, if I took the derivative of cosine, I'd get negative sine. So that means an antiderivative of sine is going to be negative cosine of x, evaluated now between pi and 0. So that's going to be negative cosine of pi minus negative cosine of 0. That's going to be negative, negative 1, plus cosine of 0 is 1. 1 plus 1 is 2. The area in one bump of the sine curve is 2, exactly. Kind of crazy. Now, sometimes people say, well, what about that plus c? Why can I just take negative cosine x? Why don't I need the plus c? Let me just show you. If I did the integral from 0 to pi of sine x dx, and I used my most general antiderivative, so negative cosine of x plus some constant c, evaluated between pi and 0, then what I would get is what I get at pi minus what I get at 0. So that would be negative, negative 1 plus c minus negative 1 plus c. Awful lot of negatives in here. So let's see, this would become just 1 plus c minus negative 1 plus c. Okay. Now I'm going to distribute that negative. So I get 1 plus c plus 1 minus c. Those c's cancel. Okay. So any antiderivative can be used in the fundamental theorem. If you're finding an indefinite integral, you're finding the entire family of all antiderivatives, then you're not looking for a specific number, you're looking for a family of functions, and you need to write the plus c. But if you're just using this as a tool to calculate this number, any member of this family of functions is a tool that will work to calculate this number.